Okay, so I just want to make it absolutely clear again for the uninitiated that the point of putting some patients in one bin and some in the other, right, based on whether or not they have a lesion. So the ones who have a lesion in that voxel will go here, the ones who didn't have a lesion in that voxel goes here, and now the t-test is going to see whether, is it the case that the ones who have the lesion there score differently from the ones who don't. And if so, the assumption is that voxel is important for that behavior. And that's really what you're doing all over the brain. At each voxel, you're finding voxels where, when you group patients as to whether or not they have a lesion in that voxel, right, you'll see a difference or you won't see a difference in their behavior. That means in each voxel, you're grouping patients differently, right? You see what I mean? You have a group of patients, and within each, because I'm just repeating this because it took me like a year to get the logic of this. So I'm assuming I'm not the only one who needs this kind of step-by-step stuff, right? So in each voxel, right, some patients will have a lesion there and others won't, and it'll be different in each voxel. So you'll have to make a new binning. You'll have to do that differently and do a new t-test in each voxel of the brain. And that's the basis of this kind of analysis.
Can I add one more group, which is like normal subject?
So that's interesting because we never...
Yeah, the answer is...
Assumption is... Right?
Yeah, the answer is you can. You can include subjects who don't have lesions anywhere. Their scores will always be in the one bin. But it's usually not a good idea because what happens is you end up, your results end up being driven by differences between people with brain injuries and people without brain injuries. That ends up driving your effects. So it becomes very difficult to identify when you see an effect in a voxel if you're seeing, if you're seeing a true difference between, if you're seeing something that's driven by differences between patient groups or between all the patients and normals. So in some sense, what that amounts to is it amounts to including a poorly chosen control group for the most part.
Could you clarify what you mean by a template when you say pick a template?
Oh, right. So the idea, this is maybe not particularly completely necessary if you're doing it by hand, but the idea is that ultimately you want to sort of show a picture of a brain and say where you had effects, and that brain has to be somebody's brain, or some average of brains. So we call it a template because it's usually something to which the other brains are mapped. We come up with some sort of relationship between each individual subject's brain and that template brain.
Okay, so then if you're looking at two different damaged brains and you've mapped the same template on both of them, you can be reasonably sure that the voxel over here corresponds to the same area, same voxel.
That's the hope. When it goes well, and patients with brain injuries are particularly hard to register correctly, but we have an approach that seems to work.
And the process you find the correspondence between the same points between different brains, that's called registration, and we will cover that
in detail.
In the third right, that's the third session. I have another question about dichotomizing lesion and no lesion. Is it always possible to distinguish, lesion and no lesion? In TBI subjects, there are like confused area where there's it's not complete encephalomalacia, but it's not completely intact. It's kind of gray area.
Yeah.
Is there anything like that?
Well, I guess there are a few issues there. So one is subtler issues in deciding where a discrete lesion begins and ends, and I think Grant's going to cover that as a practical matter next week. But the other more I think difficult issue is how to understand dysfunction in brains that's not easily dichotomized that way, and there are approaches to do that. I'm not convinced that any of them are terrific, but I think we could certainly talk about that in one of the coming weeks, I think.
I'm just curious whether it will help or just, it's a trivial matter. Or...
Well, there have been some proof of concept studies, like Ed Herskovitz did that study with I think it was attention deficit subjects who presumably have reasonably normal brains at some level. But he demonstrated that a technique that didn't require sort of eyeball identification of which area is damaged, but that was just sensitive to like intensity levels in the brain was able to identify systematic differences. And actually, the whole sort of industry of voxel-based morphometry is based on this kind of insight that you can tell a lot about what kind of structure low-level structure is in a voxel by the intensity value. It's sometimes useful.
If you had a continuous measure of how sort of damaged the tissue is in a voxel, could you do a regression instead of a t-test and then use the beta weight?
Yeah,
T-value?
we have code that does that. It works great. It's a little slower, obviously, because it's. But yeah, you can do the software to do that is available and fairly trivial. It hasn't come up that often because multiple regression comes up fairly often. So in which case you have a maybe some other non-spatial covariate of nuisance covariate that you want to factor out. So we frequently do that. It doesn't come up a lot for like these stroke studies because usually you're identifying the stroke manually, but it doesn't have to be. So there have been groups that have used continuous measures of the degree of abnormality in each voxel. And it's proven to be useful. The other thing is that when you do the registration, when you do this automated registration process, you may draw a very sharp line around where you believe the lesion is, but after you do the automated registration, there's actually a fuzzy border because that border doesn't map exactly onto voxels anymore. And so that also gives you an area where continuous values actually reflect the uncertainty in the location of the border. I don't think it tends to matter that much if you have a large enough group, but it's doable.
I assume you'll be talking about statistical thresholding later?
At some point, yeah, it'll come up a little bit today and a lot in session 4.
I'm thinking about the Rorden and Carnath data sets that you've put up, first the subtraction analysis and then the SPM method. And, you sort of made it sound like it was a definite advantage that the SPM analysis found a smaller region to be significant within a slightly larger region. And I just wanted to sort of ask you, that depends in part on your choice of a threshold.
Yeah, right. So I probably shouldn't have said that. But I guess what I really wanted to highlight there is that it can really tell you, it can in principle tell the difference between something that's evident by eyeball when you don't have any sense of threshold, and something that that appears to be statistically reliable. So, truthfully, my guess is that if they'd had 2,000 subjects instead of 150, those regions probably would have turned up. I imagine that generally, if you have damage there, you're a little more likely to have a field cut or whatever. But yeah, I think that's right.
So when you were running through this, what occurred to me is this whole issue of coverage, which I'm not sure I've ever really understood, right? So I'm sure you'll talk about that later, but can you just, so if you have a voxel and obviously like only 1 out of 100 people have damage, you really can't say, if it's 5 out of 100, you have really low power, right? So, I don't know, I just wanted to expound on that. Because that was confusing to me, thinking about that in terms of this.
Yeah, it's certainly the case. So when you do the exercise this way, power doesn't enter into your t-tests, but it certainly enters into your results in that you find a lot of voxels where you have carried out a very low power test and not surprisingly gotten not much of a result. I do have some slides on power later, and I'm going to talk about it in a little more detail in the 4th session where we're actually going to do some hands-on, I hope, power analysis. But it's a huge issue because not only because for a few reasons. I guess one is that there are some areas where you never get coverage, so where you never get good coverage. You just some areas that are rarely injured in the group that you're interested in, and this can be a problem. Although Chris Rorden has often written and said that he feels that that's not as big an issue as people make it out, because if these areas where primarily responsible for the deficit, then that you're observing frequently, then they would have to have been injured frequently. But it certainly could be the case that these areas
Could be complementary to the.
yeah, or that you just don't know what a reliable deficit is because you've never seen these areas damaged. The other thing about power is that if you need to compare when you look at a statistical map, and actually I have a slide on this later where I can point to something, but if you look at a statistical map, at an SPM map, and you see like a hotspot over here and no hotspot or what looks like a weaker hotspot over here, it's really difficult to tell by eyeballing it because the information is not there, whether that difference is because you had much better power over here or whether it's because there's a genuine difference. And this is the most tempting kind of way to misinterpret data in all of imaging. People do it constantly. Even people who've been doing this for years are always look at these maps and say, looks like you have an asymmetry there. Not that it's reliable, we don't know, but it's always the second impulse to qualify it. So I like talking about power, so it'll come up again more.
On the symptom side of this, is there an ideal type of behavioral data here, or how flexible are we in terms of the type of behavioral data we can use in VLSM?
Well, I'm going to defer to other people in the room for most of that question, but I will say that right now most of these models are not well suited to multiple dependent variables. So we don't have the equivalent of like a MANOVA or whatever. Sometimes you can turn that analysis backwards and get some results that are useful, but not always. But in terms of doing things like transforming your behavioral data, I think other people in this room know more than I do. Does anybody want to comment, please? No?
I mean, it's really, in my experience, it's really all about, do you have a good, reliable measure? I mean, that's really the most important thing. Because again, if you don't, then it's reducing your power. You already start out with, a procedure that's power hungry. So.
And that you have some measure that has variability to it.
That's right, and that has variability in the distribution. That's right.
Well, based on the steps there, right? The crux of the statistical test you're running is a t-test. So the same issues that you would normally think about when running a t-test apply here.
Yeah.
So you're going to end up with two groups for every voxel. You're going to want the variance for those groups to be scored as similar. It's the usual. So that's probably not true.
So, this may be a weird question, but when you do this analysis, you're testing every voxel in the entire brain.
Well, everyone where at least someone is damaged, is injured.
Okay, so I'm trying to just relate this to our paper where the reviewer was saying we didn't have the PCA patients. Enough of patients who had back down.
That's right. So this is this is exactly what Erica was asking about coverage, right? So in order to have these bins in which you have some patients with a lesion here, some patients with a lesion here, and you're comparing their scores, their performance on the scores, right? You don't want to have an empty bin here, right? If you have an empty bin here, you can't say anything. And the thing is that when we start out by selecting our patients who have aphasia, right, we're typically selecting for people who have lesions, who have had strokes in the middle cerebral artery. And that means that there are going to be parts of their brain, right, that tend not to be damaged. So if we were to look at those areas, we wouldn't have any patients with lesions in them, right? And so we can't say anything about those posterior areas that are covered by the posterior cerebral artery, right?
So even though we know their behavior is probably not going to be.
Well, exactly, we can't know. I mean, if you're looking at something subtle, right? So we were looking at semantic errors. So what they're saying is those areas could be important for semantic errors, and you just wouldn't know it because you haven't looked at patients who have damage there, and so you can't know that.